position. So you never have quadruple points. Only triple points. Okay, those triple points you see there, and there. Okay, the triple points again correspond to a triangle. So those triple points, okay, these are the corners. Okay, those triple points here correspond actually to a triangle. Okay, each edge of the Voronoi diagram here correspond to an edge of one of the triangles. Okay, and those edges are orthogonal together. Okay, this edge is orthogonal to that edge. Why? Because the Voronoi edges are the orthogonal bisectors of the line connecting the two seats. Okay, and again, to each Voronoi cell correspond one, okay, and only seed. Okay, so you see, this thing is what I call the geometrical dual. So to a Voronoi diagram corresponds a triangulation. So the Voronoi diagram fills the whole space, and this triangulation, so that's a triangulation, fills the convex hull of the seats. So I am going to erase all my ugly drawings here. Okay, so you see here this geometrical dual. You see here that this triangulation, okay, fills the convex hull of the set of points, okay, and this triangulation is called the Delaunay. Triangulation. This is the Delaunay triangulation. This is the Voronoi diagram. So Delaunay triangulation and Voronoi diagram are geometrical duals. And you can go from one to the other pretty easily. So it means if I have a Delaunay triangulation, I can build the Voronoi diagram. If I have the Voronoi diagram, I can build the Delaunay triangulation. For example, imagine that you have the Voronoi diagram. Okay, I have the Voronoi diagram. I don't have the Delaunay triangulation. What can I do? If I have the Voronoi diagram, what can I do? I can just draw. Okay. The Voronoi diagram, I have here triple points. Okay. So for each triple point corresponds to 3 seats. Okay. And so each triple point corresponds to one triangle. So get all the triangles for the triangulation, just getting all the corners of the so there are as many triangles as there are corners in the Voronoi diagram. Imagine now that I have the Delaunay triangulation. How can I build the Voronoi diagram? I compute all circumcenters of all the triangles. All the circumcenters of all triangles corresponds to the corners of the Voronoi diagram. And then how can I build the Voronoi diagram? I choose one seed. I look for every triangle that is connected to that seed here. And I connect their circumcenters. And what do I get for each seed? It's Voronoi cell. So if you have the Delaunay triangulation, it's super easy to compute the Voronoi diagram. If you have the Voronoi diagram, it's super easy to compute the Delaunay triangulation. It means that those objects are actually same objects. Okay, they have the same complexity, they have the same information, and you can easily go from one to the other. The good news here is that it's easier to build the Delaunay triangulation directly without constructing the Voronoi diagram. So that's the good news. So most of the time, if you want to compute a Voronoi diagram, in small dimensions, dimension 2, 3, or 4, then what you do actually is you build the Delaunay triangulation and then use the dual property, the dual argument, to go from the Delaunay triangulation to the Voronoi diagram. So it's what everybody would do in computation in geometry. Okay. Again, Fortune's algorithm in 2D is the fastest one, and it's quite complicated. Here, I'll show you how to build Delaunay triangulation in any dimension, meaning that I can build Voronoi diagram in dimension 3, 4, 5. Another byproduct of that algorithm is that because Delaunay triangulations are able, in fact, are constructed triangulation of the convex hull, then if you can build the Delaunay triangulation, it's easy to find the convex hull using any data structure to store a subdivision, like for example, the half-inch data structure. You can work in the triangulation, and if you find in the triangulation any edge here that has only one triangular neighbor, it means this edge is on the convex hull. That's it. So if you have the Delaunay triangulation, you have the Voronoi diagram, and you have the convex hull. That's nice. So how do we build Delaunay triangulation? First, that's obvious here. You see that any triangle that belongs to a Delaunay triangulation is said to be empty. That's a little bit strange as a word, but we say all triangles are empty. What does it mean? It means that if you take the triangle and you draw its circumcircle, this circumcircle is empty. It doesn't contain any point. Of course, you draw the circumcenter, okay, and you just draw it like so. This is my circum disk, if you want, okay. The circum disk is empty. It means it doesn't contain any point. It doesn't contain the point of the triangle because I consider the open set, not the closed set. So I consider, okay, it's circum disk, and inside the circum disk you don't have any point. That means that this situation, okay, is actually impossible. So why is it easy to prove? Imagine you have a point Pi that belongs to the circle. So the circle is not empty. What does it mean? If you look now at our Voronoi diagram, here, imagine we have this point, and I'm going to change of color so that you see, we have this point, okay? And if a point was on the circumcircle, was somewhere here, it would mean that it would belong in one of the Voronoi cell of either that point, okay, excuse me, again, I'll do it again. Imagine now that I draw the circumcircle of that triangle, okay? If a point here belongs to that circle, it means that this point belongs either to the Voronoi cell of that point, or that point, or that point. Or Voronoi cells, okay, only contains one point. It doesn't contain 2 points because a Voronoi cell is a set of points closer to the point than the other one. So a Voronoi cell contains only the point that is its seed. It doesn't contain any point. Which means if a point is here, this cannot be the Voronoi cell of that point, which is a contradiction. So in a Delaunay triangulation, every triangle has its circumdisk empty. So every triangle, it has its circumdisk empty. This property is fundamental because this property not only is extremely interesting theoretically, but it's the basis of every algorithm that aims at producing a Delaunay triangulation. Again, I repeat it, it's the algorithm all algorithms that wants to compute Delaunay triangulation use this property. So, there is a lot of things we can prove. We're going to prove two very easy things. But there's a lot of things we can prove. And I'll resume them. I'll make a small resume at the end of this presentation. So there's a lot of properties related to that, to consequences related to that property. First, there is something quite... So this is geometry from the Greeks. So this is geometry from more than 3,000 years. Okay, so the Greeks could have demonstrated everything that is here, because what we use here is essentially Thales' theorem, not more. It's quite interesting to see that everything that is here could have been demonstrated 3,000 years ago. It's classical geometry. So first thing, imagine we have two circles, C1 and C2, that share an edge. Okay, so this is the edge. Okay, these two circles share an edge. And so those circles, the centers is always going to be on that straight line, which is the orthogonal bisector of the segment going from Pi to Pj. Okay? So edge Pi Pj divide disk C1 into disk sectors. And so what is, you can see here, is that this sector on the right side here, the sector of the yellow disk, contains the subsector of the larger disk, the blue disk. And this blue disk on the other side, on the left side, contains the yellow sector of the other disk. So the sentence says PIPD divide the disk C1 into this sector, and one of those two sectors completely lies inside C2. Okay, and the other way around, if you look on the other side, on one side, okay, it's the small disk that contains portion of the big disk, and on the other side is the big disk contains the yellow sector of the other disk. So it's just an observation. So Delaunay edges. So what we are going to prove is that an edge of a triangulation, okay, oops, I've lost my, shit. Oh, okay, it's back. Sorry. So an edge PIPJ, so this edge, okay, of a triangulation is a Delaunay edge if there exists a circle that contains Pi and Pj, and that is empty. So it means that if you have a triangulation, and if you can find a circle that passes through Pi and Pj and that doesn't contain any point, this edge is called, it's a definition, a Delaunay edge. Okay. And so what we are going to show is a mesh is a Delaunay triangulation, so a triangulation is a Delaunay triangulation, if and only if all its edges are Delaunay edge. So again, so this is a variation of the fundamental property of the empty circumcircle, okay, of the empty circle, is that the fundamental property is a property that is related to the triangles. It can be, this property can be, in fact, can be translated into an edge property. It means that a Delaunay triangulation, okay, contains only Delaunay edges. And a Delaunay edge is an edge where it's an edge where you can draw any circle, okay? Not any circle that passes through its 2 points. It's not a circle, it's just ugly, okay? But that's my circle, okay? If it contains a circle that is empty, it's a Delaunay edge. I don't tell you that you have to take the circle of minimal radius or whatever circle you want, okay? You can if you can find one circle, then it's a Delaunay edge. And what we are going to show is that a Delaunay triangulation is Delaunay if and only if it has the strictly Delaunay edges. So the first part of the proof is super easy. So let's assume that we have a Delaunay triangulation, okay? Of course, if you have a Delaunay triangulation, what circle will you choose? Let's say this is the edge you're looking for, okay? PIPJ. So what we want to prove is that if you have a Delaunay triangulation, that every edge is Delaunay, that it has a circle that is empty. What circle are we going to choose? But if you have an edge, there is at least one triangle that contains that edge. Okay? So if you have an edge of a triangulation, it has at least one triangle adjacent. It is either 1 or 2. It has 1 if it's on the convex hull, it has 2 if it's inside. But anyway, there is at least 1. And because of the hypothesis that it is a Delaunay triangulation, the circle of every triangle is empty. Which means that what is the circle I'm going to choose? I'm going to choose the circle corresponding to the adjacent triangle. This one is empty, and this one passes through PI and PJ. So it's okay. First part of the proof. The second part of the proof is a little bit. Why is it doing that? Okay. Second part of the proof is a little bit more complicated, and it involves the first stupid property of two circles that share an edge and that, in fact, have, I would say, either on one side, one of those two circles contains the circle area, and on the other side, this contains the other circle area. It comes with that property. So we assume now that every edge of the triangulation is Delaunay. Okay, so it's the second part the third part of the proof. Every triangle is Delaunay. So every edge is Delaunay. We've proved that. Now we prove that every edge is Delaunay. Then every triangle is Delaunay. So every edge of the triangulation is Delaunay. It means that every edge has an empty circle. Okay? We are going to prove it again by contradiction. We assume that this triangle here, PI, PJ, PK, is not Delaunay. What does it mean? It is one point that lies inside his circle. So the point cannot lie inside the triangle, of course, because it wouldn't be a triangulation. Okay? So the point has to lie in one of the two disk sectors. That is, I will show you the three disk sectors. Okay, for example, this is one of the. Oops, this is too big. Oops. Let's do that. Okay, so this is one of the disk sectors I'm talking about. Okay. Okay, that's one of these. We assume it lies inside this disk sector corresponding to edge PI, PK. We assume that. By hypothesis, this edge PI, PK is a Delaunay edge. So it doesn't have any circle, which is empty. So you should be able always to draw a circle that passes through PI and PK, and that is empty. Okay, so assume now that, of course, we draw a circle that is on that side. Okay, but this circle, as we said, contains this whole portion, this whole section of the disk, which means that it cannot be on that side because it's supposed to be empty, but this side contains point PL. But of course, we could draw a circle on the other side. Okay, a circle here on the other side that is not containing, okay, not containing PL. But of course, this circle contains PJ. So it's a contradiction. So I just proved to you that it's impossible to find if the triangle is Delaunay, it's not Delaunay. You cannot find a circle corresponding to its edge, its edges. So it means that if it's not Delaunay, so no empty circle for edges, okay, which means that if you have not A implies not B, this is equivalent to B implies A. Oops, okay, remove that. So it's a logical it's a standard argument of contradiction. Okay, you prove that if you have not A, then you implies not B. That proves that B implies A, which means that if every edge is Delaunay, then the triangles are Delaunay. So these are the two ways of describing a Delaunay triangulation. First, every triangle has an empty circle. It's equivalent to say that every edge of the triangulation has an empty circle, any one. So, what we can talk now is local Delaunay root. And that will lead to a first algorithm that allows to build a Delaunay triangulation. So, imagine we have an edge here. And two adjacent triangles. So this edge is internal. It's not on the convex plane. So this edge is internal. What this edge is said to be locally Delaunay if you take the circumcircle of one of its neighboring triangle here, and this one is empty. Okay? What you see here is that the circumcircle of this triangle that I just draw, okay, is not empty. So this is not an edge that is locally Delaunay. Of course, why do we say locally? We choose a specific set of circles. But what we can prove is that that this argument is symmetrical, which means that if this edge is not locally Delaunay with respect to this circle, it's not locally Delaunay with respect to the other circle that correspond to the other triangle. Okay, it means that this circle contains PL and this circle contains PK. So if you have two triangles like that, okay, if I take the circumcircle, so two triangles here, if I take the circumcircle of this triangle, which would look like that, okay, if it contains that point, this edge here is not locally Delaunay. And this property is symmetrical. It means that if now I'm drawing the circumcircle of the other triangle, this one, okay, then it contains that point. The green circle contains the other point. So it's a symmetrical property. What is really interesting is that if you have an edge that is like that, not locally Delaunay, so an edge that is shared by two triangles, then if you replace that edge by, so these two triangles form a quadrilateral. Imagine a quadrilateral with PJ, PK, PI, PL. This quadrilateral has two diagonals, that one and the one in dashed line. If this edge, PJ, PI, is not locally Delaunay, what you can do is flip it. Replace that green edge by its the other diagonal of the quadrilateral. This is the edge flip operation. Edge flip operation, what you can say is that you can guarantee that if you flip an edge that is not locally Delaunay, the new edge here is locally Delaunay. What you can prove too is that if every edge is locally Delaunay, then of course every edge has an empty circle that corresponds to one of its two neighboring triangles. So we've proven that. So if every edge is locally Delaunay, then you have the Delaunay triangulation. So we can imagine a first and nice algorithm that would produce a Delaunay triangulation. We start with a triangulation. Of course, that's not obvious to create a triangulation. I'll show you a very ugly way to do that. So imagine you have a triangulation that is not Delaunay. Then, by applying flips to every edge of the triangulation, then you attain with a number of flips, which is a maximum number of, if you have n point, n square flips, you will go to the Delaunay triangulation. Okay, so that's a first algorithm. It has lots of theoretical implication. One thing you could say to me, what happens if we have that, if the quadrilateral is concave? If the quadrilateral is concave, you cannot do a flip, because what you would have is two triangles here, one here and one here, okay, that actually overlap. So as I tell you, a triangulation, by definition, is a non-overlapping set of triangles that actually exactly cover the convex hull of the set of points. So if here you apply that flip, you have overlaps, so it's not a triangulation anymore. But if the good thing with the Delaunay triangulation and with the flip algorithm is that, in fact, if you have a concave situation, any concave situation is Delaunay, is locally Delaunay. So if you have concave quadrilateral, you cannot have the circumcircle of that triangle, in fact, that contains a point. It's easy to see that, in fact, the two circles, okay, can never, okay, contain the other one. So the circle relative, let's say here, to Pi, Pj, Pl, can never contain points Pk. Okay, so you can always do. So the edge flip algorithm is robust. It will only apply when, in fact, it's not locally Delaunay, and when it's not locally Delaunay, it's mandatory that the two triangles that share that edge are forming a convex quadrilateral, so you can flip. And you think when you have flipped, you change from a situation when the edge is locally Delaunay to an edge not locally Delaunay to an edge which is locally Delaunay. So the algorithm, as described, must finish. Okay, because at any time you find a Delaunay edge, you make it a non-Delaunay edge, you make it a Delaunay edge. And the algorithm stops when every edge is Delaunay, which means that when you have the Delaunay triangulation. What is quite profound, a quite profound consequence, lemma, from this result is that every triangulation is flip connected. It means that you can find any triangulation of a set of points, any one, okay? You can go from any triangulation to any other triangulation only using flips. How do you do that? Let's add a new slide. Okay. So imagine you have triangulation T1 and triangulation T2. You can go from T1 and T2 to the Delaunay triangulation. That is unique. Why? Because Voronoi is unique. So if Voronoi is unique, the Delaunay triangulation is unique. So you can go to T1 and T2, two different triangulations, you can reach this Delaunay triangulation by doing flips. So you have, for example, to go to T2 to T1, you have a sequence of flips, okay? So my sequence of flip is going to be F1, F2, just Fm. You use M flips, okay, to do that. And so, if you want to go to T2 to T1, what do? You go to T1 to the Delaunay triangulation, and then from the Delaunay triangulation, you do the reverse sequence of flip. You unflip the last, you undo the last flip by unflipping, and then this one, and then this one, and then so you do the inverse sequence of flip. You do the inverse sequence of flips, and then you go to T2. Means, again, that when you do a flip, you don't change the number of triangles, okay, because you replace two triangles by two other triangles. You don't change the number of points, okay, and you don't change the number of edges. You replace an edge by an edge. So we just show that every triangulation has the same number of triangles, has the same number of edges, if we consider triangles of the same set of points. So what I just proved here is that if you have a set of points, P1 to Pn, every triangulation of the set of points has the same number of triangles, same number of edges, okay? And we are going to compute that number. It's quite easy to show how much you have triangles there. So another thing is, how would you build a first triangulation? How would you build a first triangulation? Okay. Imagine I take a first point, I take a second point, and I take a third point. Okay, I do first with the three first points, I do a triangle. Can I always do a triangle? Yes, because points are in general position, so they are never co-circular. Okay, 4 points are never co-circular, making the Delaunay, the Voronoi diagram unique, and so the Delaunay triangulation unique. Second, 3 points are never aligned. Okay, so if you take any triplet of points in your set, you will never find, in fact, the triplets that are not able to do a triangle. So we have 3 points here. And imagine a fourth point. Imagine it's here. What do? I do that. Fifth point there, I do that. Point here, what do? I look to every edge of the current convex hull, okay, and I look in which of the Voronoi cell it contains. So this is the edge that is actually the one that actually sees that point. So I do that. Okay, and if I'm here, okay, I'm going to look here, here, and I'm going to do that. Okay, and that. Okay, again and again, we can continue to build this triangulation easily. Okay, so what does it mean? It means that I'm creating here a very, very ugly triangulation, one of the most ugly objects you can do. What do? Then you apply the flip algorithm to that triangulation, and you get the Delaunay triangulation. It's certainly not the best way of producing a triangulation, because as I tell you, there is a maximum of n square flips. Okay, you could be as far as the Delaunay triangulation as n square flips. So a flip is, let's say, one operation. So if you have a set of edges, you just loop over all the edges, and you look at if you have to flip them. And in the worst case scenario, you would have to flip n square edges to get to the Delaunay triangulation. So it's a bad algo. So this is the flip algorithm. As I tell you, it converges at most n square flips. You can prove it's easy. It's quite easy to prove, to find, in fact, a scenario where you exactly need n flips. So it's the worst case scenario. And you can also find the second part of the proof is that you can always go to the Delaunay triangulation in at most n flips. Okay, so there's two parts of the proof. One which says there are, in fact, bad triangulation when you need n square flips, and the other side you will never need more than n square flips. Okay, that's it. So that's what I said. The reason is of utmost important. It means that every triangulation is connected to the Delaunay triangulation. So it means every triangulation is flip connected. That's what I told you. One little remark here, of course, the bad part of the flip algorithm is not that it's totally inefficient. It is also only available in 2D. In 3D, it's not available, but it's not available, and it may never be available. There are open problems in computational geometry. In computer science, I would say that half of the open problems come from computational geometry. There is a lot of open problems, a nice open problem in computational geometry. One is the following one: are triangulation in 3D, mean tetrahedrization. Okay, the extension of a triangulation in 3D is you have a set of points in 3D and you connect them by tetrahedron. The question I could ask you is: are all tetrahedrization flip connected? You can flip edges also in 3D. The answer is probably no. So most of the researchers, including me, in the domain have good evidence that the answer is no. I have no proof. If anybody does approve of that, it's a major result. But for today, the consensus in the scientific community says that in 3D, we don't know if the tetrahedrization are flip connected, but the answer is probably no. They are not flip connected, which means that there is no flip algorithm in 3D. Because if there is a flip algorithm, it means that you could go from any tetrahedrization to the Delaunay tetrahedrization, which is unique if points are in general position in 3D, and no 4 points that are coplanar, okay, and no 5 points that are co-spherical. Okay, it's the same notion, but in 3D, there is no flip algorithm. Okay, there's no Fortune algorithm to construct the Voronoi diagram, and there's no flip algorithm. It doesn't mean we don't do flips, okay, but we don't do flips to construct the Delaunay triangulation. So, this is an illustration of the flip algorithm. You start from a triangulation, which is, again, a triangulation is always a set of triangles that exactly covers the convex hull, non-overlapping, okay, and that actually covers the convex hull. Of course, if you remove that triangle, you still have every point which is inside, which belongs to the triangulation, okay, but it doesn't fill up the convex hull. So if I remove a triangle, I will remove one triangle and one edge, but this is not a triangulation anymore with my definition. So this is not possible. So we start from here, and the algorithm is super simple. And if you use the data structure that I have presented you 2 or 3 weeks ago, which is the half hedge data structure, doing flips is an extremely simple local operation inside a data structure. It's extremely simple, and again, it's a triangulation because you don't change the number of edges and the points and the triangles. It's just flipping numbers. Okay, you don't add or remove anything from the data structure, which is super easy. Just flip numbers. Flipping is just flip numbers, and then you're done. And it's very, very, very cool to apply this thing. So what you can do, it's one of the possible things you could do, and as a project, is to do the flip algorithm. Why not? I don't say I say it's not efficient, but you could do that. What you do is you have a list of edges. Okay, you have the list of edges of your triangulation. You loop over all the edges, and you look if, let's say, for example, that edge is locally Delaunay. How do you do that? Okay, you compute the circle of its neighbors, and you look if this point belongs to this circle. Of course, this, again, I told you that the predicates in computational geometry are very important. We looked several weeks ago at the orientation predicate. You have 2 points and a third point, and you look if the sign of the area of this triangle. This was called the orientation predicate. I've given you a set of predicates as a C++ piece of code, if you remember well, and then Professor Legas, the link was kind of broken. Now it's not broken anymore. So you have those predicates in the website of the course. So you have the orient 2D, okay, takes 2 points, P1, P2, and a third point, P3, and tells you if the area, the signed area of the triangle. You have another predicate which is in circle. In circle takes 3 points, P1, P2, P3, and a fourth point, P4. So it takes here, if I'm looking here, you would give P1, P2, and P3 here, and a point P4. And the in circle tells you if P4 lies in the circle with P1, P2, P3. There is a major robustness problem if you do that by hand. So if you compute the circle, it's not complicated. You compute the circumcircle position here, okay? And if you look if the distance between the circumcircle and P2 is larger or smaller than this distance. And you could answer the question like that. This is very non-robust. For the same reason I explained weeks ago, you've got epsilon machines, you get round-offs, and those operations essentially ask for computing a determinant in 3D of a 3x3 matrix. And this determinant, of course, when you compute a determinant, sometimes you have an elephant, you have minus another elephant, and you have a mouse. Okay, you have a big number, you subtract another big number, but you want to have a lot of precision on the small number that is the result of that. So it means that if the point that you look is very close to the circumcircle, this operation is not robust if you don't pay attention. So this thing I gave you as, I would say, a piece of code, you don't have to look inside what is inside it. It implies, again, as I told you, to go to very high precision numbers. So you go to quadruple, sextuple, octuple precision, and so you have to. This is kind of complicated, and it passes through filters. You first have to use the standard formula, and you have to assess that this formula give you a good result. If you're not sure, then you go to multiple precision. And so this is always the same kind of logic. And if it lies exactly on the circle, you have to do something to, because we cannot have an answer, I'm exactly on the circle. You have to be either outside or inside. So this function always gives you a systematic answer, okay, a robust answer, saying it's either outside or inside. So what you do again in the flip algorithm, I do it again, you look at that edge, okay, that edge, you use the in circle predicate, asking if this point lies into the circle of that triangle. The answer is yes. So what do? You say, I'm removing that edge and replacing that edge. And I do it again. I'm looking at that edge, for example. Oh, it's not Delaunay. I'm flipping it. Okay? And I'm looking now at that edge. Oh, it's not Delaunay. I'm flipping it. Again, again. And at some point, when you reach to that triangulation, you know that all edges are locally Delaunay. Okay? So it means this is the Delaunay triangulation. So this is a first algorithm that is actually simple, not efficient, but it actually produces a Delaunay triangulation. Of course, you have to build the first one. And I gave you a very crude and super bad initial triangulator. Okay, that's what I would do. But in fact, what we're going to talk about now is the good way of building the Delaunay triangulation. But at first, I'm not going to prove that thing. So it's in my notes. If anybody wants to have a proof of that, it's quite a long proof. But this is an amazing property. It's an amazing property. What does it say? It says that the Delaunay triangulation is angle optimal, which means that the Delaunay triangulation gives you nice triangles, beautiful triangles. So what is in quotes this property? If you take all the triangles of your triangulation and you take all the angles, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, okay? So you will have alpha 1 up to alpha 3 multiplied by number of triangles, okay? You've got as many angles as 3 times the number of triangles. And you sort those triangles such that alpha 1 is the minimum. So alpha 1 is the minimum angle of all the triangles. So if we look here, for example, alpha 1 could be that one here, okay, on this triangulation. Maybe that one. But on this last triangulation on the Delaunay, alpha 1 may be, if I'm looking, maybe that one. Okay, this is alpha 1. What do you see here? It's the alpha 1 of that triangulation is way smaller than the alpha 1 of the Delaunay triangulation. But that's not something, it's not a hazard. It's not hazard. It's the property. It's the main property of the Delaunay triangulation, the main geometrical property. It means that the Delaunay triangulation among all possible triangulation, and the number of triangulation is not infinite, the number of triangulation, but it's combinatorial. So it's related to what is called Catalan numbers. That tells you how many triangulation you have. Okay, it's not obviously it's not the all possible combination of 3 among n. It's not that. So you cannot choose any triangle, of course, because some overlap. Okay, but there is a finite number of triangulation of a set of points, super large. But among all those triangulation, now every triangulation you could find, the Delaunay triangulation, unique Delaunay triangulation, is the one that maximizes alpha 1. It maximizes the smallest angle among all triangulations. Why is it important? For many things. It's important in geometry, in geometry processing, if you're doing, for example, Delaunay triangulation and you want to color things, etc. But it's very important for interpolation. If you do finite elements, and most of you, all of you have done finite elements, if you have a triangulation and you want to, you put values of a function, okay, at the node. Okay, you put, and then you interpolate that function, okay, on every triangle of your mesh, creating a discrete interpolation of the function. And there is something you have not seen in the finite element course. You know, again, I have a proof on my note of that, but it's not. It would take 2 hours to do it. But what you can prove is that if you are measuring the norm, okay, of the gradient of f, the true one, minus the finite element interpolation of the gradient of f, okay, and you put it in 2 norms, okay, measure what is called Dirichlet energy, something like that, and it's bounded by the norm of if you do P1, okay, of the second order derivative in 2, okay, it's a Hilbert, it's a Sobolev norm, but anyway, it doesn't matter. Here, there is here EH, which is the largest edge of the triangulation square, not square, it's H, and you divide that by sinus of alpha 1. Okay? So what does it mean? It means that, of course, you don't want to have very large, the largest edge you have, of course, the worse is the interpolation. But here, you don't have significant difference in the edges of that triangulation with respect to that one. But here, if alpha 1 could be arbitrarily small in a bad triangulation, which means that you could, if alpha 1 is very small, then this thing could go to infinity. So if you have triangulations where you don't control the angles, and you refine it in a very stupid way, by not controlling the angle. For example, if I take that triangle, and I refine it like that, then I refine it like that, then I refine it like that, what do we get? We get triangles where, in fact, H doesn't change. So you don't expect to have a better interpolation, but it's even worse. Alpha 1 is getting as small, arbitrarily small. And what happened in this case, you cannot interpolate anything. So finite element don't work, because this is the first thing. What you do when you want to do finite element proof, first you assume that you have a good interpolation scheme. And second, you just prove that the finite element approximation is better than just the finite element solution is better than just interpolating the field and the nodes. Okay, that's the usual way to prove that the finite element method works. You first need approximation interpolation theory that doesn't need finite elements. You take a function and you put the values of the function at the nodes, and you compute a gradient using the finite element shape functions. Okay, that's what you do, and you look at the difference between the actual function continuous and your discrete value, and that's the interpolation theory. That's quite complicated. Then after, you can prove that this object, which is the exact solution approximated, put it at the node, is worse than a finite element solution. And that you have the proof. But here, if you have bad triangulation, it's not, that doesn't work. Of course, if here sinus alpha 1 can be 0 if alpha is 0, but it's also 0 if alpha is 180 degrees. Okay? So you hate infinite elements. Very small angles, but that's not true. Small angles. So this thing is way too conservative. Okay? What can be proven is that, and that is true, that the small angles are not that important. It's the large angles that are important in finite element solution. So in finite elements, you actually accept those kind of triangles. Those kind of triangles are kind of okay. But those kind of triangles, so that is called a needle. The needles, it's okay, it works. But the cap, the hats or the caps, that is super bad. And so it a little bit contradicts what I told you just before. The Delaunay triangulation allows to not have small angles. But it is not the Delaunay triangulation, the triangulation that actually minimizes the largest angle. No. And there is no algorithm to build this min-max triangulation. So a min-max triangulation would be the triangulation that would be loved by finite element practitioner, because it would minimize the maximum angle. And the maximum angle is the one that we want to control if we want to have good interpolation properties of our scheme. And there is no good algorithm to build min-max triangulation. They are all n-squared. Yet, when you have a triangulation that has a good alpha 1, which means that it maximize the minimum angle, you have a good chance not to have large angles, because the sum of the angles of a triangle is 180 degrees. So if you don't have very small angles, then there is a good chance you will not have large angles neither, but you cannot prove it. So you could have Delaunay triangulation, for example, with obtuse angles. And again, obtuse angles have a lot of drawbacks in finite elements. If you have obtuse angles, for example, if you do Laplace operators have local maximum properties. If you have the solution of a Laplace equation at a point, okay, it's inside the domain. The solution at a point cannot be neither maximum or local maximum or local minimum. And if you have triangles that have all acute angle, no obtuse angle, then if you do finite element solve Laplace equation, then you will have this maximum property fulfilled by the discrete scheme. And it's of very high importance when you do simulation. For example, if you need that scheme, if you want to you don't want overshoots in your temperature, if you come to temperature field, or overshoot in the pressure. So having good triangulation has a large impact on the quality of the finite element solution, and the Delaunay triangulation is not that bad. In 2D. In 3D, it's not true. Again, flip arrowing doesn't work in 3D, and the max-min property has no equivalent in 3D. So in 3D, Delaunay triangulation are ugly. They produce tetrahedra that are Delaunay, but that have volume that can be arbitrarily small, which means that they can have you can have a tetrahedra that has a volume which is arbitrarily small, but that doesn't have a very big circumsphere. So again, 3D, if anybody tells you that in computational geometry something is, the extension in 3D is easy, I would just be careful about that. So what is the good algorithm? So I didn't tell you that there is no algorithm to build the Delaunay triangulation in arbitrary dimensions. I just tell you that the Delaunay triangulation in higher dimension doesn't have the nice property. They are not strip connected, and they don't have I would say, geometrical beautiness in higher dimension. But they can be constructed efficiently in any dimension. And this is the algorithm. So the algorithm here is not a sweep line, it's not a divide and conquer, as we've seen. It's purely, I would say, incremental. What is an incremental algorithm? The incremental algorithm I present you here works like that. At first, you assume that you have a Delaunay triangulation with n points. Okay, so dt n, the n here is n points. And you want, in fact, to build the Delaunay triangulation of n plus 1 point, so the n first point plus a new point. So you want to add a new point in the triangulation. What I'm going to show you here is that the operation is most of the time local, essentially local. So what do? You have a Delaunay triangulation here. This is dt n. And I'm going to add a point here. Okay? What do I do? First, you must acknowledge that there is a certain number of triangles that will be removed. Which triangles? The triangles that have their circumcircle containing Pn plus 1. And so those triangles are here in pink. Okay? That thing is called the Delaunay cavity. And so what are the properties of that cavity? The Delaunay cavity 1, okay, C of dt n Pn plus 1. This is the Delaunay cavity corresponding to the Delaunay triangulation dtn, where with the addition of Pn plus 1. 1 is star-shaped. will recall you what is a star-shaped poly. It's a poly. It's connected. This first property, this property, it's connected. So it's in one piece. It's not in several pieces. It's in one piece. It contains the point, of course, okay? Because the triangle where the point lies obviously has its circumcircle, okay, containing the point, because the circumcircle of a triangle contains the triangle. So the point, so it means that the cavity contains the point. It's connected, so it's not in two pieces, it's in one piece. So it's a its boundary is a polygon. Okay, it's star-shaped. I'll explain you very, very important. And point P n plus 1 belongs to the kernel of this polygon. So it's star-shaped, it means it has a kernel, and the new point is inside the kernel. So this is the thing. This is a polygon, okay? What you see here is a polygon. The kernel of a polygon is the set of points that actually see all edges, okay? From this point, it's not in a kernel, because if I'm looking at that point, I cannot see it because it's hidden by that face. So this doesn't belong to the kernel. Okay? So the kernel can be constructed by simply taking every edge, oriented, look to the right, and say, I'm taking that one, and then taking that one to the right. If I'm intersecting all half planes, okay, sequentially, with respect to all the edges of the polygon, I get, or I don't get, a zone which is called the kernel of the polygon. Of course, the kernel of a polygon which is convex, okay, is equal to itself. There are polygons that don't have a kernel. If I draw you that, this one doesn't have a kernel. If you take an intersection of all half planes, then you're done. Remember, it's the first algorithm that presented you is to find a triangulation of a polygon. The first thing to do is make it, okay, make it star-shaped, okay, because when it's star-shaped, it's easy to triangulate. What it means, if you have a polygon which is star-shaped, that has a kernel, okay, there is a super simple way to triangulate it. Super simple. Take any point of the kernel and then do that. Because we see all the points, those triangles that I create will not overlap. So if you have a polygon which is star-shaped, take any point of the kernel, draw lines with respect, create triangles with respect to all the edges of the polygon, you have a triangulation with one internal point. And so, what can be proven is that if you are constructing a Delaunay triangulation, you are constructing, first is Delaunay cavity. And so the Delaunay cavity is star-shaped. And Pn plus 1 is belonging to its kernel. So, Bowyer-Watson algorithm works like that. Take a new point, Pn plus 1. Find its cavity. The cavity, what is the cavity? It's a set of triangles. Remove those cavities, remove those triangles from the actual triangulation and replace them by the triangles formed by, in fact, triangulating the empty cavity using that simple procedure, just connecting this point with all edges of the cavity. What can be proven is that doing that, you conserve the Delaunay property. So doing that, the new triangulation that you get is dt n plus 1. So that's the procedure, okay? You remove, that's the Bowyer-Watson algorithm. So this is exactly what you do. You compute the cavity, You remove all the triangles in pink here. Then you triangulate the cavity. You know that you can always do that because of it can be proven you can always do that. It means that you don't have to check anything. It will work. It will produce a Delaunay cavity. It will produce a triangulation, a valid triangulation of the Delaunay cavity, and it's Delaunay. So the algorithm works like that. Start with an initial triangulation, and then add the points one by one. Okay? That's absolutely amazingly simple. Is it that simple? So that's how it works. So how do we do in practice? We compute first a bounding box, an axis-oriented bounding box of the set of triangles. Okay? Of the set of points. And we extend it a little bit. And we initiate our Delaunay triangulation with two super triangles. Of course, here you would tell me, oh, the points are not in general position. Those 4 points are co-circular. Yes. So what you see here, if points are co-circular, Delaunay triangulation is not unique anymore. Because if you have a quadruple point here, okay, you could either choose that edge or that edge. Those are two possible Delaunay triangulations. So Delaunay triangulation is not unique anymore. Okay, doesn't matter that much. So you choose that one and it's okay. Okay, and then add the points. Okay, iteratively. We add that first point first. Okay, and then we create those triangles. And then we add this new point. This new point was what was the consequence of adding these new points? These two triangles here were removed. Okay, and then we have created a new triangulation. And again, and again, and again, and again, up to that point. Then, at the end, we need to do some edge flips, but a very few amount of edge flips to recover the convex hull. Okay, that's pretty easy to do. Okay, what we don't want is that there are triangles, there are actual triangles of the mesh that actually are concave, okay, on the boundary, because I want to remove that one and that one that correspond to that one. Of course, this is a concave corner. I don't want that, so I do an edge flip and I get it. Okay, I get this edge flip and I'm done. Okay. That's it. That's the formula. dt k plus 1 is the old one. Remove the cavity. Add the triangulated ball. And that's called the Delaunay ball. Those are names, of course, they don't have, it's not very important. But this is the name that is usually used in literature. Okay. This algorithm looks simple, but there is a difficulty if you want to make it efficient. But it's possible to make it efficient all the time. And the way I'm going to explain it to you is different from the book, because in the book, I think this is something which nobody uses anymore, so I'm not going to explain what is in the book. I'll just tell you in 2 words. So, Bowyer-Watson Algorithm, what does it do? Imagine that is dt k, okay? Triangulation with k points. And this is pk plus 1. That was the last point we added. So, one thing which has to be done is to find the triangle here where the new point lies. And from that triangle, we can do what is called a breadth first search, which means that if you have a triangle, you know the union point is inside, you look at the neighbors of the triangles. And if these neighbors of the triangles, the circle contains the points, Then look at the neighbors of the neighbors. Okay, and then again and again and again, up to a point where you find your cavity. Okay, that's the idea. So here, this is my cavity that I found. The problem is, the main problem here is, how can I find the triangle that contains the point? One thing that is clever to do, and that is provably correct, is to walk. So this is what I call walking. You imagine you have just created that cavity. Okay, you have just remeshed that cavity by adding point pk. So you have in memory at the time of the algorithm of all those triangles. Okay, what do? You can, and that's the main idea. I'm going to put a new slide to show you. Okay. Okay. You have a triangle here. That is your initial triangle. Okay. And you have p k plus 1 here. What do? You look here in the three directions here. Okay. Here, in my case, of course, what you take the centroid of that point and you look at that vector. And this is, let's say, v1, v2, and v3, and this is d. Okay. You take d dot v1, okay, d dot v2, and d dot v3. Okay. v1, v2, and v3, of course, are unit vectors, and they are orthogonal to the three edges. And they point outside, of course. And you take max of these three vector products. This max corresponds to here v1. So you know you should go in that direction. And so you have a new triangle here. Okay? Then you do it again. You get here, here, but you, of course, don't look back. Okay? You get here and here. What is the maximum? Maybe it's that direction here. We go there, and then it will go there, and then it will go there, and then it will go there, and at some point, you will go inside the triangle so you will walk like that into the mesh, like that. And so this is a true case here that I showed you. What can be proven again, if it's a Delaunay triangulation, then Delaunay triangulations are said to be acyclic. It means that doing that walk, you could never go back to your initial point and do cycles. So it looks strange that things like that could happen, but it could. If you create really strange triangulations with very small angles, there are simple examples that where you can create cyclic triangulation. It means that you could cycle by yourself and go back, which means you will never find pk plus 1. You will do a thing which will do like that. You will never find it. It never happens. Anyway, even if you don't have a Delaunay triangulation and things may be cyclic, there are ways to do the walk in a robust fashion. So this thing can always be done. The problem here is that if you have, let's say, n points in 2D, you have square root of n points multiplied by square root of n points. And if your first point is here and your next point is here, the maximum, the worst case scenario would be that you would walk of the order of magnitude n to the power of 1 over d. This is the dimension of your problem, okay? So if you assume that the size of a cavity is pretty much constant, which is the case, okay? The size of the cavity is in 2D, I'll show you, it's pretty much constant anytime you have a point. So when you have found the new triangle that you have, and you have found the triangle where lies the new point, creating the cavity, the number of operations is constant. Okay? So if you want to add n points, you would have to walk for each point and then insert the point. So you would have n points, And at any time you add a point, you would have n to the power 1 over d walks in the worst case scenario. So your algorithm will be n to the power 1 plus 1 over d, the dimension. So in 2D, it's n to the power 3/3. This is bad. Of course, it's better than n squared. It's better than n squared than the flip algorithm. But still, it's super bad. Because you want to have something which has the complexity of Fortune's algorithm, which is n log n. Because if I only have that algorithm, I would never use this Bowyer-Watson algorithm in 2D, because I would create the Voronoi diagram, compute its dual, and I would do that. Yes, but the idea is that, and I'll show you how it works. What we want to do is sort the points in such a way that when you have two consecutive points that you add in the triangulation, these 2 points are close. And a very naive way to do that would be to sort the points with respect to, like you did in your other algorithm, you sort the points using, let's say, their lexicographic coordinates. So you sort first by x and then by y. But imagine that you have points that are like that here. So this is the first one, then the second one, then the third one, which is quite far, and the fourth one is super far, and the fifth one is there, and then the sixth one could be there, seventh one there, eighth one there. It's really bad, okay? Because if you sort first by x and then by y, it's bad. You could try to sort with respect to their distance to the origin, but again, it would be extremely bad, because you could have a point here, then a point there, which is at the same distance, but at 180 degrees, and etc. So sorting in a very naive fashion will never work. There are algorithms and way of sorting points in such a way that most of the time, 2 points that are consecutive in the list are always close together. How do we do that? We do that using what is called a Hilbert curve. So this very strange drawing is just a set of 1,000 points, and we sort them and we put a line between 2 consecutive points. So you see the points are sorted in such a way, a little bit like that, okay, and there, and here. Okay, they are doing that. How do we do that? We must introduce the concept, which is a geometrical concept, of space filling curves. Space filling curves. What is a space filling curve? You know what is a curve. A curve is a mapping from, let's say, a 1D domain, 0, 1, onto, okay, let's see, 0, 1, t, onto the curve C, okay? Here, at each parameter t corresponds here x of t. Like that. That's a curve. Usually, you assume curves are objects, of course, of dimension 1, because they only depend on one parameter. But we can imagine curves which are of dimension higher than 1. Those are called fractals, you know that. So fractals are curves of infinite length, okay, usually always of infinite length, which have a fractal dimension, okay, which is, you could see the fractal dimension of a curve as, it's not really a 1D object, it's not 2D, it's between 1 and 2. But there are curves which actually can fill that can pass through every point of, let's say, a unit square. So if this is a unit square, I can build an object which is called a space filling curve. That is fractal of dimension 2, exactly 2, which means that at the end of the process, the curve will pass through all the points of the domain. One very stupid thing would be do is to do that, okay, and that, and that, and that, and that, and that. That's called a Z-curve. Okay, you could do that, and then do more wigglings, and if you do an infinite amount of wigglings, okay, then at the end, it's like a coloriage, you would fill up the curve. The point here is this is not a curve that we are looking for, because we would like a curve that actually fills the unit square, but which preserves locality. Here, that's not bad. It doesn't preserve locality because this point, the next point is at the other side of the square. And then this point, the other point is at the other side, and the other side, other side, other side. So this point doesn't preserve locality. There are curves which actually conserve locality. They have a lot of application in computer science, storing data in memory or things like that to preserve locality. This is, if you have, let's say, your memory is actually a 1D thing, and if you want to, if you have a 2D, let's say, 2D structure you want to make conserve locality, then you like to use such kind of curve that are 2 or 3D. There is the same construction in 3D, so a little more complicated. So if anybody wants to do the Delaunay triangulation in 3D, then I will give him the Hilbert sorting piece of code that actually wants to do the 3D. I will give him the sort machine that actually sorts the point in 3D in Hilbert fashion. So what is the Hilbert curve? The Hilbert curve is a specific space filling curve. And the construction is like follows. You start with that pattern, okay, on the unit square. So what is actually that pattern? That pattern actually allows us to number the quadrants, the 4 quadrants of that unit square. So this is 0, 1, 2, and 3. What is important to understand is 0 is close to 1, 1 is close to 2, 2 is close to 3. Then you apply this pattern recursively, but if you look here, every quadrant is, and I change the color, every quadrant, choose other colors here, every quadrant here again is split in 4, but we do rotations of the initial pattern. So you see here the initial pattern is rotated here from, let's say, minus 90 degrees. Here it's just copied, here it's just copied, and here it's rotated by, in fact, here, plus 90 degrees. Okay, so here minus 90 degrees, here plus 90 degrees, and here idem, idem. And we link them together like that. So if now I'm removing all this scratch here, and we do a nice thing. So this was our initial split, and then here we split it in 4 again. And so this was the first quadrant, 0, 0. This is 0, 1. This is 0, 2, 0, 3. And you understand this is 1, 0, 1, 1, 1, 2, 1, 3. Again, here I'm entering it's 2, 0, 2, 1, 2, 2, 2, 3. And here we have 3, 0, 3, 1, 3, 2, 3, 3. So the Hilbert curve it's a beautiful object, and you see that this is nice, but it's totally useless. The drawing the curve is just for having a beautiful figure. The Hilbert curve is just there to number quadrants. So here, the idea of the Hilbert curve is that if you put a point, any point, for example, I could put a point in, let's say, here, okay, it's extremely easy to find in which quadrant it is, okay? And if I can compute that this point belongs to 2, 0, that's its Hilbert coordinate. So if you sort the points with respect to their Hilbert coordinates, 2 points that are consecutive will be close together because of the locality of the Hilbert curve. So that's how we do. We take a set of points and we assign to every point its Hilbert coordinates. The Hilbert coordinates are those, let's say, bits. And we compute here, we compute 2 bits. Here we need 3 bits. Here 4 bits, 5 bits, and I don't know, maybe it's 8 bits here, or 6 bits, I don't know. So as many bits as you have, the more bits you have, the more precision you have. Because every point that lies in that quadrant, if you only use 1 bit, has the same Hilbert coordinate. Here, of course, every point that is in that quadrant or that quadrant has the same Hilbert coordinate. But the more you go deeply, the more coordinates you compute, the smaller the quadrant will be, and the more precise will be your computation. Of course, this is a naive thing. Usually, people would use adaptive number of coordinates. Okay, but in a simple explanation that we have here, that's how we do. We fix at the beginning how many coordinates we want to use, 6, 8, okay, and then we compute for each point of the set you want to triangulate its Hilbert coordinates, and then we sort every point with respect, all the points with respect to their Hilbert coordinate. Then 2 points that are consecutive in the list will be close geometrically, which means that if you sort the points and you apply the naive Delaunay triangulation algorithm, the number of walks that you are going to do will not be of the order into the square root of n, will be constant, which means that the actual algorithm, the Delaunay algorithm, when the points are sorted, is linear in time. Yes, it's linear in time. So where comes the n log n? Sorting the points. Sorting the points, it's always requiring n log n operation, but when the points are sorted, the Delaunay triangulation is in linear time. So I told you it's impossible to find an algorithm which is better than n log n, but here, in recent work from my team, my research team, we have devised a way of sorting the points in a very smart fashion, where we use that kind of concept and we can sort 1 billion points in a fraction of a second, which means that the sorting part of the algorithm is so fast that you never see the n log n aspect of the algorithm, because triangulating 1 billion points cannot be done on a machine. It takes too much memory. Okay, so you can sort 1 billion points, but triangulating them requires more than a computer. So it means that in practice, the Delaunay triangulation of a set of points is linear in time, because the sorting part can be just avoided or neglected. So how do we do in practice? And maybe I've been talking now for more than an hour and an hour and 30 minutes without stopping. So my proposition is that we are going to stop for today, and next week I am going to do a live coding of the Hilbert curve in 2D. So I'm going to really do a live coding stuff of from scratch. Given a set of points, I will do the code that actually does that computation of the Hilbert coordinate. It's not easy at all. It's pretty simple, okay? And it's a matter of 25 lines of code. And of course, I'm going to use the sort function from the C++ library. I'm not doing the sort by myself. I'm just going to compute the Hilbert coordinate of a given point, okay? And then compute, let's say, compute it for, let's say, 12 or 15 bits. And the bits, it's not bits because there are four different states Okay, and in 3D there's 8 different states, and I'm going to show you how to do that, and I'm going to show you results to show you that we can triangulate 1,000,000 points in 3D in less than a second on a computer. So if anybody wants to use that algorithm as his project, I would advise you to download from I'll show you the website, our implementation of that triangulator, and compare with it, because I think we have the best implementation existing of that thing. We've been working a lot on that. So I'm going to stop for today. If anybody has questions, please open your mic and ask. I'm going to move to the other one. Oops. No, not that one. That one. So this is the code. I promised you. This is the code. But next week I'll do it live. Anybody has questions? No questions. No questions. You can also ask a question in the, okay, there. Not for me, yes. Yes, I can give you the slides now. I'll give you here. Oh, no, by mail, because some people. So the slides are not that different of, the first part is from the previous week, so I continued, and I added the new one. So I can send it to you now, the slides. Okay. 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 Done. They may change again next week because I'm creating them on a. I already gave the slide to May, but these were the old ones. The last 10 slides are not from next week. From last week, it's different from last week. They are new. So it's on the mail. So you have it now. Okay. You have it. Any other questions? 1.5 seconds for Delaunay triangulation 1,000,000 points, fast enough. In 2D, yes, it's very fast. In the book, in fact, they use a different scheme. They use in fact, when you do a Delaunay triangulation, you see, you create new triangles, and all the time. You start with 2 triangles and then you add points, okay? 2 super triangles, then you add points. What happens is that you could remember the whole set of triangulation that you have done. Okay, so you have a triangle is replaced by 2 elements. So you could have like a hierarchical structure, and you could do a search of the point inside this hierarchical structure, starting from the 2 initial triangles, going to the second triangulation, third one, fourth one, and get to the, let's say, k+1 triangulation. So normally with that, okay, you can go in order of, I would say, the power of 2 that is required to have the number of triangles to search. So it's an n log in base 2 of n to get the point. The thing is that it requires a very complex data structure, and it's way slower than the implementation I propose. Other questions? Okay, so I'll leave you, and we do the next class next week. Okay, bye-bye. Have a nice week. Okay.